In this video, I want to do a couple of things. So the first thing that I want to show you is so again, I'm going to revisit everything I did from the previous video, which is we implemented a MUX 4-to-1 by instantiating three 2-to-1 MUXes that we have previously defined. And I want to show you an alternate way to instantiate. So what we're doing right here is called implicit instantiation. So we are relying on the fact that we are passing the signals in the order in which they have been defined in our 2-to-1 MUX. And that is performing the correct mapping for us. So in this case, my 2-to-1 MUX defines these four signals, S, X0, X1, and Y. And in my instantiation, I am passing, probably this would be a better example, my selector S is going to be S1, my X0 will be Y0, my X1 will be Y1, and my output Y will be also Y. So I'm relying on the fact that I am providing this comma separated list of signals in a particular order. So if I want to, I can pass them in any order I like. I just have to tell Verilog what I'm doing. So for example, and let me give you an example here. If I wanted to tell Verilog explicitly, you know what, in my 2-to-1 MUX, my input S is actually going to be my signal S0 over here in this top module. So to be clear, this dot S refers to the input S from my 2-to-1 MUX, and what's in brackets is the signal that's declared in this module. So it has scope in this module. It's understood only within this module. And that is the name of the signal that I want to be mapped to signal X that's inside the 2-to-1 MUX. That's a port of the 2-to-1 MUX. So over here, I'm going to pass it, and I can't remember, it was X0, right? So I have to, this relies on me knowing the names of the ports, whereas the other way relied on me knowing the order of the ports. So implicit instantiation relies on me knowing the order in which the ports are declared in the module I'm instantiating, and explicit instantiation relies on me knowing their names only. So I am going to pass back here in my 4-to-1 MUX, 4-to-1 MUX, X0, this will be X1. And I cannot mix, as you can see from my error, I cannot mix implicit and explicit instantiation. So implicit instantiation is when, as it says here, my ordered port connections, I'm passing them in the order that they're defined in the module I'm instantiating. And a named port connection is the explicit instantiation way, where I'm naming the port according to the names that are in the module I'm instantiating. So I'm going to fix that error by doing this. And now that wavy line goes away. So I can leave only this one, and now I'm actually getting another error, which is because I am missing an ending parentheses. So know that whenever I open a parenthesis, it has to be matched by an ending parenthesis. It always needs its pair. So so I can leave this one, my first MUX 0, to use this explicit instantiation using named ports, and I can leave the others to use implicit instantiation relying on port ordering. So I'll maybe just do one other to show you. So again, what this is telling Verilog is, hey, you know that port S in MUX 2 to 1? Well, I want to pass it the signal S1. And you know that port X0 in MUX 2 to 1? I want that to be mapped to Y0. So what is this doing? This is really like when you're wiring something up on a breadboard. What I'm doing now is I'm placing a wire between my input port, in this case S1, and the pin on an IC that's a MUX 2 to 1 that corresponds to S, the selector. So it's really like I'm just wiring things up together, except now I'm doing it conceptually instead of physically on my breadboard. So this is explicit instantiation. So that's the first thing I wanted to show you. And you know what, why not? I'll just do it for all of them just so that you can see, and then I'll show you the elaborated design, and nothing should have changed. And in fact, I see that actually nothing has changed at all. Everything is as it was previously. Okay, so that's the first thing that I wanted to show you. Okay, and the other thing that I wanted to discuss with you is this issue of having to pass so many different signals. Like this really becomes cumbersome and unwieldy, especially when my signals can be logically grouped. So you'll notice that, you know, signals x3 to x0, they're 4 bits representing a single, you know, logical data set. And same with my selectors, S1 and S0. They're actually 2 bits of a single logical entity. And there's got to be a better way. So for example, here I have a 4 to 1 MUX, but imagine I had an 8 to 1 MUX or something like that. And then I would have to take the time to write out all these different signals, one per bit. And wouldn't it be great if, similar to what I do in a bus, where I can logically group wires, each carrying a single bit, but then just refer to them logically by the same name? Wouldn't that be great if I could do that also in Verilog with ports? And in fact, I can do it with any kind of signal. I can do it with wires as well. So this concept is called vectorization. So what we're seeing here are scalar quantities that refer to a single bit. So each one of these refers to a single bit. But what I can do is I can have something like this. So what I'm going to do is I'm going to remove all these guys, and I'm going to replace it with a single signal X, except this signal X is going to be 4 bits wide, sorry. And in fact, it's going to be referred to from most significant, which is traditionally like bit 3, all the way down to least significant bit, which is traditionally bit 0. So what I'm going to do is I'm going to denote that with these square brackets right before my the name of my signal. And I'm going to specify a range of bits here. And the way I specify a range is I start with the most significant bit, I put a colon, and I follow it with the least significant bit, which is 0. And this tells Verilog I am creating a signal called X, but X, instead of being a single bit wide, is 4 bits wide, and furthermore, X goes from 3 to 0, where 3 is the most significant bit and 0 is the least significant bit. And now I'm going to do the same with my selector. So I'm going to have a single selector signal, but my selector signal now is going to be 2 bits wide. And again, the way that I denote that is my most significant bit will be bit 1, and my least significant bit will be bit 0. And so this allows me now, instead of having to write this module declaration so many different times, I can just write it twice. And in fact, if you recall, when you added a design source, you had the ability, so I'm going to create a new 4:1 MUX, but I'll call it new MUX 4:1. And you'll recall that when I was asked to specify my port names, I could actually specify it as a bus. And I can furthermore specify the MSB and LSB. So I'm going to go ahead and do that. So I'm going to recreate exactly what I did. I'm going to show you that this is going to produce the same code that I just manually wrote. So I have my signal X. MSB is 3 and LSB is 0. Now, of course, nothing is stopping me from creating another range. I can do, 7 down to 4 is also a valid range. But I mean, unless there's some compelling reason, otherwise, I'm going to keep my LSB to be 0. And then my MSB will be however wide I need the signal to be. So the second port is simply called S for selector, and that's also a bus, and the most significant bit is 1. And finally, I have my output Y, which is a scalar. So I will not check off bus. And if I click OK, it is going to create this new file, new MUX 4:1. And you'll see that actually I have the same module declaration as I did when I wrote it out manually. So that's this. Okay, so I'm going to dispense with this. So I'm just going to work with this file because I've already written the code for it. But now you'll see that actually I have to change this code over here, because now I don't have a signal called S0 or X0 or X1 or S or X2 or X3 and so forth, or S1. So I don't have these signals anymore. They don't exist. So how do I refer to individual bits in this bus? And the way that I refer to it is by their index. So S0 now is simply the signal S, but I want to refer to the 0th bit in X, and this is how I do it. So now notice it's a bit tricky because when I was defining the signal, the square brackets with the range came in front of the signal name, but now when I'm referencing it, first I have the signal name, and then I have the square brackets with either the bit number or the range that I want to reference. So I can also reference a range here. However, MUX 0 is expecting a single bit. So I am going to pass a single bit, which is the 0th bit in the bus X. And similarly here, this is going to be the 0th bit in the bus X, and this is the first bit in the bus X. And I'm just going to make those modifications here. So this is semantically slightly different because now I am not referring to scalar signals. I'm referencing individual bits in a vector signal. And this is how I reference them. And anybody who's done any high-level programming will recognize this type of array indexing. So I need to modify the Basis 3 master to reflect my new top-level port names. So I'm going to open up my Basis 3 master file, and I've replaced it with the default one provided by Digilent file. So I know for sure that I need 6 switches, 4 for my X and 2 for my selector S. So that brings me to switches 0 to 5. I'm going to use my trick of doing control / to uncomment in a block. Now I'm going to go down and do the same for my single lead that references my output Y. Now I'm going to show you a trick here. So up until now, what I've been doing is every time I change my top level port names, I go into the constraints file and I change the names of the ports in the constraints file. But what if I tried to make my life a little bit easier and I said, you know what, all I'm going to do with the constraints file is comment and uncomment things. And where I will change stuff is in the top level file where I will change the port numbers in my Verilog file to reflect what I have in my constraints file. So that's what I'm going to show you how to do here. And it's going to make it so much easier because now that you understand vectorization, you are not going to need to change anything in the basis master file except for commenting and uncommenting those ports that you need or those pins that you need. So notice that in the basis 3 master file, my 6 switches are already, so these are the port names, and notice that it has already vectorized the ports for me. So it's as if it's expecting in my top level module that I should have a signal called switch, SW, and it is a vector, and because I've only uncommented these lines here, it is expecting it to be in the range 5 to 0. So this is the first thing that I'm going to do over here. I'm going to come here and I'm going to remove these. Actually, I'm going to comment them. Oops. I'm going to comment them. And what I'm going to do is I am going to, I'm pressing caps lock instead of tab. So I am going to declare instead an input, which are my switches. And I know that I have 6 of them, and they range from 5 to 0. And I declare this in the opposite order because, of course, when I'm declaring it, I put the range first. I know it's a little confusing, so even I get confused. So I put the range first and then the name of the signal. And the name of the signal as the constraints file expected it is SW first switch. And what about my output? So I'm going to leave this here and I'm going to go back and look at my output. And I only have a single lead, but it is vectorized. I'm referring to lead 0, which is saying take this bus named lead, this bus signal called lead, and take the 0th bit of it. So how am I going to declare that in my MUX 4 to 1? I'm going to say output, and I actually have a vectorized signal, so I do need to put the square brackets with the range, and the range is just from 0 to 0. Y. Lead, sorry. Okay, but now you'll see that in my code, I'm referring to these other signals that are not declared. And in fact, I'm getting this error, right? So signal S is not declared and X is not declared. So let me fix that. So I'm going to declare a wire that has 4 bits, X, and I'm going to assign it directly to the rightmost 4 switches. So switches, and again, so when I'm referencing something, I put the name of the signal first, but when I'm declaring something, I'm telling Verilog for the first time about the signal, I put the range first and then the signal name. So I know that's a little bit confusing, but keep that distinction. So you need to keep the distinction between declaring something. So declaring something is telling Verilog about it for the first time. which is what the wire keyword and the input and output keywords do. They're telling Verilog about these signals that it hasn't seen before. But when I'm referencing something, I'm referring to a signal that has already been declared. So switch has already been declared in the port declaration up here. So the signal name goes first. And now I'm going to reference the range. So I want switches 3 to 0. And finally, I have my 2-bit selectors. So by convention, I'm going to keep the least significant bit 0. However, they refer to the switches 5 to 4, right? 5 and 4. So how do I reference that? So recall how I declare a range, which is I put the most significant bit of the range, then a semicolon, and then the least significant of the bit of the range, and everything goes in square brackets, and of course is terminated with a semicolon. And now my code should work. So I'm going to go ahead and save my files and elaborate the design. Okay, so I've come to show you that I come to look at my elaborated design, and this is useful because I made a mistake. I never mapped my LED to Y. So in fact, look what happened here. I would never have caught that mistake, by the way, if I hadn't gone to look at my elaborated design. Or actually, probably when I ran synthesis and implementation, I would have gotten a warning. But now look what's happening. I've got, this is a clear indication something's wrong. I've got my lead floating here, and I have nothing coming from the output of my second MUX. Otherwise, of course, what I did want to point out to you was that everything else looks the same, much the same as it did before. So I am going to go back to my MUX 4-to-1 code, and I'm going to remedy this problem. I'm going to solve this problem. But this is a good learning opportunity for us to understand the kinds of things that can go wrong. So I'm going to declare a wire called Y, and I'm going to assign it to the 0th bit of my LED signal. And of course, there is only a 0th bit of my LED signal. So that's that. I'm going to save that, and I'm going to re-elaborate my design. So here's my re-elaborated design with my error fixed. Okay, so what I want to show you about this is first of all, that my switch here is declared as 5 to 0. And the 4th bit of the switch is going into this MUX. That's the selector S0. I have mapped the 4th switch to S0. And then bits 0 and 1 are mapped to my X0 and X1 respectively. Finally, again, this is selector S0, which is mapped to switch 4. And now I have X2 and X3, which respectively are what I used to call X3 and X4, right? So my 3rd and 4th switches from the right are these two. And then finally switch 5, which is mapped to what I used to call S1. That is going into my 3rd MUX, and the outputs of my 2 previous MUX stages are going into this 3rd MUX as well. And the output is mapped directly to my LED.